Good morning, good afternoon, and good evening, everyone. Thank you for attending this new semester's combustion webinar. So I'm one of the co-chair of the technical committee. My name is Wenting Sun from Georgia Institute of Technology. So today is our great pleasure to have Professor Markus Kraft from Cambridge University and to give us a talk on carbonaceous nanoparticle formation in flames. Professor Markus Kraft is a fellow of Churchill College, Cambridge, and a professor in the Department of Chemical Engineering and Biotechnology. He is the principal investigator of C4T, the Cambridge Center for Carbon Reduction in Chemical Technology. Professor Kraft obtained his PhD at the University of Kaiserslautern in 1997. In 1999, he became a lecturer in the Department of Chemical Engineering, University of Cambridge. He has a strong interest in the area of computational modeling and optimization targeted towards developing CO2 abatement and emissions reduction technologies. So welcome, Professor Markus Kraft. And now I hand the microphone to you.
Wenting, thank you very much. It's a great honor for me to be able to give this seminar to all of you. So title is Carbonaceous Nanoparticle Formation in Flames, or how is soot formed in flames. And I will present work that's been done by my research group over the years. The slides that I show tonight have been put together by Jacob and Gustavo, Kimberly, Angiras, Laura, and Maureen, and but also other members of my group have contributed to it. So right, and off we go. Here are they. I hope you remember this. This was the Diplom Symposium, and was a very nice symposium. And here you see many of the people who have contributed to the results of this talk. Okay. This is where I'm in Singapore, and in fact, I'm talking from Singapore. It's now 10 minutes past 10 in the evening. This is the Create building where we have our labs. This is where I normally live under normal circumstances. And HARES is the Cambridge Research Lab in Singapore, and C4T is the program that we've been working on. So, okay, so this is what this talk is all about. It's about the formation of soot, and we are very familiar with it. Now, okay, we know, or we believe, that carbon black carbon soot has an adverse effect on climate change. So we observe the warming of the northern hemisphere. We observe that it speeds up the melting of glaciers. We have seen changes in precipitation in Southeast Asia. So there is a strong indications that soot plays here an unfortunate role. This is further supported by a document by the IPCC, in which they distinguish between black carbon and organic carbon. Both have adverse effect. So black carbon, soot, you know, here you see this emissions from this ship clearly contributes to the positive radiative forcing, and organic carbon has the adverse effect. It's actually cooling, so they sort of at least mitigate one another, but clearly they do have an effect. So other reasons to look at these particles and to try to avoid them is their impact on pollution, and you can see on this graph that is almost not a single organ in our body that is not affected by small particles. And I think it is impossible to talk for 40 minutes without mentioning Corona. So I thought here is the slide. There are people who argue that this virus links to aerosols, and through that it is distributed. So although this is not 100% certain, it seems plausible. So this is also one aspect of particle formation. Now, I did talk about corona. If you look from the sky, basically from a satellite onto planet Earth, you can look at the PM 2.5. And if you did that in 2019, you saw something like that. And in 2020, you see that the PM 2.5 is strongly reduced. Although this is only a snapshot and may not be completely representative, we do know that because of the lack of air travel, that the particle pollution has been reduced significantly, which is a good thing. However, if we move from Earth into the solar system, we will also find evidence for soot. So now, almost 10 years back, we were approached by the Arizona Lunar Lab, and they interpreted the data of the Cassini missions, and they had the little probe Huygens, who was shot into the atmosphere of Titan. This is a moon of Saturn, and in that moon you have soot raining from the sky, and they did some extinction measurements, and we helped to interpret and derive the fractal dimension of the soot particles that rain from the sky. But even if you leave the solar system and you look at the Orion Nebula, you see that there is evidence for PAHs, the building blocks of soot particles, as we believe, and hopefully that's what I argue later. So there's soot all over the place, and it's not only harmful, it's also an important industrial product. I just want to mention two areas: the pigment blacks. So it's used for printing inks, in plastic, in paper, in the construction industry, and it's not only used for inks, but also as a reinforcement materials, in particular in tires. That's the main area of application. And 90% of all carbon blacks actually are for the rubber industry, a very important industrial material. So now I have hopefully argued that there are a number of reasons to understand the formation of soot better, to understand how the properties evolve. I can formulate a problem statement. And of course, combustion is a science that is quite old. So Palmer and Cullis argued in 1965 paper, and I quote, "A major breakthrough in understanding carbon soot formation will have been achieved when it becomes possible in at least one case to account for the entire course of nucleation and growth of carbon on the basis of a fundamental knowledge of reaction rates and mechanisms." Right, and this is what this talk is all about. I will come up with a few hypotheses, and I will sort of give you a fast run through our activities and put them into perspective with other people's work. Right, so some of you remember the soot meeting in '94 in Heidelberg, organized by Professor Bockhorn. I was just starting my PhD under his supervision, and this was a schematic that you find in the front of this book. It's a Springer book, and that depicts the then understanding of how soot formed. Now, 26 years later, this view, this view has been refined. Okay, so so my student Dake put this beautiful big figure together, and so we start from the fuel pyrolysis. We are able now to identify specific structures and then have some sort of nanoparticle formation that form into primary particles and then the aggregates. What is different between then and now is here on the right side. These are super important experimental pieces of work done by various groups that really pushed our understanding enormously. Each of these bullets is worth an own invited talk, and I just want to put these things out, these contributions out for reference. The only work I would like to mention specifically here is the high resolution AFM work by Andrea Danner, Julie Wohnert, and IBM groups. Okay, and this work has produced these beautiful molecular images, which for the first time give us some evidence that some of these PAHs are in existence and play an important role as a precursor for soot formation. Right. So in my own research group, I also did some work, experimental work. So we are interested in the sooting propensity of fuel. So one fuel is not like the other. We started with a smoke point lamp and developed a more accurate way of determining the smoke point using fuel uptake rate measurements as a threshold. Here, this is Roger and Maria who will play an important role in this talk. And then more recently, we've been looking at powder fuel and the role of 5-member rings in combustion. And you will see later in the talk why we were looking into 5-member rings. My postdoc, Jochen Dreyer, improved the inverse Abel transform that you need for color ratio barometry so that he could reduce the noise in this measurement technique. This is a cheap way of getting estimates for soot volume fraction and temperature, and that has been quite successful. And I cannot talk about sooting propensities of different fuels without mentioning the fantastic work that has been done at Yale over more than 2 decades in this area. This is just a pointer. I don't want to say more. I will get into detail later. Right, so what I will do in the following, I will talk about soot modeling, and I will basically cover a lot of time and a lot of length scales without going into details what each of these methods mean. I will mention it as I go along when we use the methods, okay? So the first and most important contribution of my research group is the development of the stochastic particle method. And this represents soot particle in unprecedented detail. We start describing the particles type space, that is the mathematical representation of what a soot particle is. Most particle models are very simple. The type space is just mass and maybe surface area. Here, we really zoom into the particles. We look at the aggregate. We look how this aggregate is connected to primary particles, okay, through this adjacent matrix. Then each primary particle in turn is made of molecules, okay? It has a position, it has a radius, and then these molecules are then composed of a list of carbon atoms, of functional sites, a connectivity list that lists the carbons that are on the outside of the PAH. We have then the atom coordinates. We know whether a carbon is connected to any other atom. We know whether a carbon is either on the fringe of a pH or not. And with that model, we are able to formulate reactions that happen on the functional sites of such a carbon. The functional sites in turn are expressed in the following way. Here are examples: free edge, zigzag, armchair, 5-member rings, embedded 5-member rings, partially embedded 5-member rings, okay? And through this system, we can formulate a whole reaction scheme, okay? Here is an example for some early work. Oops. right? So what you see here, this is work Michael Balthasar, who spent in 2004 some time with Michael Franklach, and as a collaboration, we developed this first detailed aggregate model, which allowed us to basically represent the aggregate structure of such a particle. And many iterations later, just recently, exchange student from Tsinghua University, Ding Yu, came over to Singapore in our labs and then used our latest particle code to reproduce premixed flames, soot particle formation in premixed flames, and we were able to represent the primary particle distribution as well as the aggregate distributions. Now, Ding Yu, see her here, very able student, now starting a postdoc at UCL. She also developed a model to basically calculate the coagulation efficiency and derived a Lennard-Jones potential of the constituent atoms in the two particles. She used a simplified model for these atoms, but it was good enough to improve the coagulation efficiency and get a better prediction of the size distribution. But it's clear, if we want to understand what the particles are made of, we have to have a better understanding of the precursor chemistry. Now, the problem with the precursor chemistry is that pHs, they grow. And of course, you may all be familiar with the classical Kempkin mechanism format, where you have, you know, a species, each species is formulated as a differential equation, and you have a coupled set of differential equation that describes all the species. If you did that with pHs, you will very quickly find that the mechanism, the number of species you needed, grows completely out of bounds. This is why you cannot really simulate gas phase chemistry of pHs if you want to really also take into account larger structures with the classical detailed chemical mechanism approach. For this reason, we developed the kinetic Monte Carlo method. Again, you have so many reactions that can take place. You have to introduce some simplification. And what we've done, my student Gustavo has sort of published a paper in Combustion and Flame, where he basically uses a combined steady state partial equilibrium approximation to make sure that the detailed chemical reactions and the reactions of the KMC models are close enough to give good results. Okay, so with that chemical model, we can now look at individual steps. And one of the steps that was of great interest to us was the partially embedded 5-member rings and how they can integrate heptagons. Okay, and this is the reaction coordinate for the reaction energy surface that has been produced by my student Angiras, and we then looked at this reaction and formulated it into the kinetic Monte Carlo code. And this is a simulation here on the right, where you see how the embedded 5-member rings allow the formation of the heptagons and create this grain boundary here that can also be found in glassy carbons. If you then calculate the mass spectrum from these simulations, you see that you can indeed find these structures in experimental work. Okay. So now where we have some sort of an idea how you can model the growth of single aromatics, the next question, of course, is how do the nanoparticles form? And what you see here is sort of one of the big pictures that were popular in another soot workshop in Naples that was organized by Andrea Danner, Edel Seraphim, Haiwang, and Professor Bocon. And it was a wonderful workshop, and I'm still glad that I could attend. I think many of you will have fond memories of it. And one outcome was that we looked at both physical and chemical mechanisms that lead to the formation of these particles. So the question is, how does that work? Okay, so now I had a student, Tim Totten, and at that time there was Alston Mesquita from theoretical chemistry in Cambridge. So we decided, okay, let's work out a potential that is able to describe the dispersion forces. So we came out with a non-isotropic potential, which we then fitted to the isotropic case, and this potential is called isoperhap. And Laura Pascaccio, who was then in Andrea Danner's group, looked at a number of potentials and created different clusters. And from these results, you see that the cluster from the isoperhap looks pretty much similar to what was observed in actual high resolution TEM measurements of similar clusters. Okay, so that gives us confidence that this potential does what it's supposed to do. And then there are two more important pieces of experimental findings. That was the Grotier group at DLR in Stuttgart. They had this wonderful mass spectroscopy, and they saw this multimode representation. And Grotier argued, okay, this must be dimers and trimers and so on. And from this and work that was done by Maria and Houston Miller, we sort of concluded that the building blocks in soot should be about 15 aromatic rings. Okay, so now of course you can then take these building blocks and use the potential and calculate the equilibrium constant. So everything that above here leads to a dimerization, everything is below is not a dimerization. So you can see, you know, this 15 aromatic ring structure is about here where the blue line is, okay? And at temperatures of 1500 typical flame temperatures, you needed much larger pHs to actually stick together, which basically indicates that a pure physical dispersion inception mechanism is unlikely. Okay, something is wrong, we need to carry on. Okay, nevertheless, okay, we looked at these clusters and try to understand how they form, how they stabilize, what structures do they take. And I have this student, Kimberly, she's just about to finish and submit her thesis if her supervisor was actually to read her PhD thesis. That would be me in this case. And she put mixtures of coronene and circumcoronene together, put it into a potential pot, and looked how these molecules would arrange over time using replica exchange molecular dynamics. Okay, I explain this in a second. Let me just move on. So what you see here are two simulations at low and high temperature. And what you do in regular replica exchange molecular dynamics, you do every other time step, you swap the structures from high to low temperature, and you hope that through this swap, you are allowed to access all different states so that you're not get trapped in local minima. Okay, it looks very nice. And what you can then do, once you have done this, okay, now I want to see the next slide, you get then low energy representation of these clusters. And so these are clusters containing 100 molecules of different sizes. This is what it looks like. I don't want to describe it here in much more detail, but the bottom line here, what I want to say is that A, B, C, and D represent the previous different initial conditions of different degrees of mixing when you start. And after a while, you see, after a very short transition period in each of these configurations, you see that the red line and the blue line stabilizes, and what you see is the radial distance from cluster center, which basically means that you get, now look at this figure, that you get a demixing. Okay, the smaller particles are all outside, and the bigger particles form sort of the core of that particle. So we have a core shell structure. Unfortunately, and now we are back. So this is some work Maria has done. When you look at the high resolution TEM and you look at these fringes, you will see that, yes, you also get the core shell structure, except that the particles have the smaller molecules in the middle and the larger molecules in the outside. So just the opposite of what was found in the molecular dynamics. Nevertheless, okay, we carried on and we were looking into even larger structure with even more types of molecules. And for that, we had to develop a different computational method, because replica exchange molecular dynamics is too expensive. So we used the Monte Carlo method, and this is called sphere encapsulated molecular dynamics. And you basically take a cluster apart, put spheres in, and then do Monte Carlo rearrangement, and then find the optimal configuration, energy configuration. When you do this, you avoid interlocking, ring interlocking, and nasty situations that you see here. This work was done mainly by Peter Grancic and finished by Kimberley. So these are the different clusters. You can now see we have different sizes and look at different configurations. And our maximum configuration contained 150 molecules and 3 different molecular types. And what we were able to do was basically to see how they order within a particle. And if you looked at the statistics over many particles, you'd see that you do get the larger structures closer to the center, and the smaller the structures are, the more they are on the outside of the particle. So far, so good. We learned from all this that pure physical forces don't describe the inception, and also the particles that you represent, that are represented, that you get through flat pHs, also don't look what we see in SUT experiments. We then looked further through the literature, and in 1969, Felix Weinberg did these beautiful experiments of counterflow diffusion flames and put them into electric fields. And once he switched the field on, he really saw a strong impact on the soot formation in these flames, and it basically stopped soot formation altogether. None of the models that we have looked at so far could explain any of that. So we thought maybe we need to look at some sort of electrical effect. So, and this is where my student Jake Martin, together with Radomir, started looking at curved PAHs. So it was clear that if you include 5-member rings, that you start curving a PAH, and the most prominent example of such a curved 5-member ring, 6-member ring structure is the Buckminster fullerene, and this is what you see up here. But you also get, once you get this curvature, a strong dipole effect, okay? And that, of course, adds another force that may be responsible for particle inception. So we were looking at different configurations, and this is what you see here. So Jake worked very hard to produce this figure and calculated with the dispersion adopted DFT method, the force between different curved clusters. And if you look at this, you see, yes, the curvature enhances the binding force compared to flat pHs, but it still doesn't quite, isn't quite strong enough to fully explain particle inception just because of this flexoelectric effect. We then again talked to Alston Mesquita and developed this Kerr type potential field. And we thought, okay, maybe if the clusters are not strong enough to cling together by the flexoelectric effect, maybe if we have an ion, this ion could stabilize clusters, which then form into soot particles. So after we had developed this potential, we looked at molecular dynamics. We seeded it with potassium ions, looked at different temperatures, looked at 10,000 coranoline molecules, and just ran the simulation. The outcome was that at lower temperatures, you did indeed see such clusters where the ion stabilizes the molecules. However, as you went to higher temperature, this effect just didn't prove strong enough to stabilize this cluster for long. Which basically meant, yeah, okay, maybe that is also not quite the explanation. So we looked in the literature for more experiments. And then again, this was Jake's initiative. He suggested to look at number indentation experiments. So at that point, Laura was in Singapore as an exchange student, and she then looked at number indentations in more closely. So what you get here is you push into the probe, and then you can measure the hardness of the materials. And if you do that for ethylene soot or diesel soot, it varies roughly between 3 and 7. Okay. So here, this group in India, they produced this wonderful video. Here is the particle, the soot particle. Now there is the indenter that pushes the particle back. You can see the load on the particle to the left here, the displacement here, and after it reaches sort of the top, the indenter is then pushed back, and you see how the indenter then goes back to its original position. And this is what remains, okay? So the idea was that Laura does this experiment using molecular dynamics, okay? And here you see an example. You see how the load is pushed on top, and you go over this tip, and then you do the whole process backwards. We used the following parameters, and this was implemented in lumps using the Aribo N potential. And from this slope, you can calculate the Young modulus and the hardness of the particle. Right. Okay. So now back to Maria. Okay. Looking at this shell core model of the particles, we thought, okay, that inspired us to produce a model particle. And this is what it looks like. Okay, so in the center, we put coronene, and in the shell, we have circumanthocene. Okay, what is important are these numbers here. So this is the overall radius that stretches from here to here. Okay, then we have the core radius, and then we have the depth of the shell P shell, okay? Another important parameter is this cross-link factor. So if Cl is equal 1, it means that one molecule has just one cross-link. If Cl is equal 2, then it has 2, it can form these chains. And if Cl is greater than 2, it can form these networks, okay? And this will be very important in the following. Right, so how did we then construct the particles? So you first have a molecular packing. There's special software we could use, okay? And then we took off the hydrogen atoms, we let the code run at different times, which formed different number of crosslinks, and then we added the hydrogens again so that everything was saturated, and they did that both for the core and the shell, and then we combined core and shell. And then we simulated TEM and looked what it looks like, and if you compare that at least by visual inspection, it looks similar. Then we performed the indentation experiments, and if you, okay, so you have the displacement up and down, okay. So if you look at the figure here, so here the radius of the core is 3.5 nanometer, and at time t equals 0, this is what the particle looks like. If you have no, this is only the core only. If you have no crosslinks, you see you just smash the particles and nothing much happens. If you have 3.5 crosslinks, then you see that the particle has quite elasticity. It regains its shape almost. And if you have just 2, it's sort of in between. Which means that for the hardness value that we measured by nanointerpretation, it varied between 2 and 8, okay, given how the crosslink and the hardness correlated from our latest experiment, we can say that the crosslink in our model soot particle has to be larger than 2.5 and less than 4, which indicates that there are a lot of aliphatic, lot of covalent bonds between the building blocks in a soot particle. Which means now we have to understand how these bonds can be formed. And if we now look at the experiments from Danner's group, there is evidence, plenty of evidence for reactive edges, for cross-linking and partial saturations. And here are specific examples that we derived from these experiments. This was a groundbreaking paper and proved enormously important to us. So now, of course, there are many possible variations of forming these crosslinks. So again, Jake took the initiative and created this beautiful interaction matrix, okay? Here you distinguish between classes and structures. So you look at sigma, real sigma radicals, you look at localized pi radicals, delocalized pi radicals, d-radicaloids, rim-based pentagons, curved pHs, and low aromaticity structures. And now we look how each structure can react with the other one. And it is clear that if you have aromatic aryl-linked hydrocarbons, you get very strong bonds, and the green color indicates that these structures can exist in flame environments. So we can be almost certain that in the flame, we will find that type of bonding. Another observation that was not so obvious from the start was that we also saw aromatic ring-linked hydrocarbons, okay? And they actually form quite a strong bond. And if you look at this structure, you can sort of see that this structure can not just be stabilized by this bond here, but also by dispersive forces. So maybe this is the ideal candidate that we've been looking for. Okay, so many people worked on this, and a lot of computing time has been spent to create this nice interaction matrix. So you see Laura, Yingyu, Yingyu, and Angeras. Now, of course, we are not the first to talk about physical and chemical interactions. If you go through the literature, you see that Harris and Reiner in '89 already said it. Miller commented on it, and in the very highly cited paper, influential paper by Frenkler and Haiwang, they say that the mass flux is likely to be driven by an irreversible process following the dimer formation and forming covalent bonded links between pH layers and having also van der Waals enhancement present. And with that, we looked at the binding energy of structures of and looked at, as you grow these dimers, what happens to the bond energy and whether or not dispersion forces take over. Now, this is a very busy figure, and I don't want you to look at all of it. The only important bits are the blue boxes here. These are the localized pi radicals, okay? And here you can see, number one, that even for small species, they're already quite stable. But as you grow them, you can see that there is a combined chemical and dispersion forces that stabilizes this dimer. Right. So the next question is: are there enough of these molecules there to be a candidate for soot dimerization? So if you look at localized versus non-localized pi radicals, you can see that if you have these 5-member rings, that the spin density does not spread out, and you keep these radicals in place. Okay, so even for larger structures, this is good news. As in comparison, if you just have an aromatic flat structure, you can see the aromaticity leads to a spread out of these electrons. So we will then, my student Angeras spend a lot of time putting a chemical mechanism for these structures together, and we calculated sort of equilibrium, and we looked at saturated, partially saturated, and pi radicals, and the important, these numbers indicate how many of the molecules from the Danner work were of that sort, and our calculations here show that the concentration of the localized pi radicals is high enough that they have a potential to play a role in the dimerization process. And so now where we have identified a potential inception species and possibly mechanism, I just want to motivate all the other mechanisms that we've been talking about. You can see there's physical ones, there are purely chemical ones, and now there are combined ones. Jake, in his thesis, has really given a wonderful summary of all this. So I encourage you to download this document. It's beautiful. And so with that, you can see basically a full characterization of the different inception paths. Also, here's a motivation of the rim nomenclature, because the bonds here go perpendicular to that rim to the other pHs, making it possible to form this pancake-like structures. And with that, I'd like to basically thank my sponsors in Singapore, and I would like to thank you for your attention.
Thank you very much, Professor Kraft. So now is our Q&A time. So I will share my screen. And before I ask the questions on your behalf, I would like to make an announcement. There will be no lecture next Saturday, which is September the 5th, because it is a holiday in the United States. And our next lecture will be on September the 12th by Professor G. Gao from Purdue University. Just keep an eye on the email. I will send the webinar information out. So now I have collected a few questions from the audience. And the first question is regarding the core shell structure of the PAH enamels. In flames, we have reactive conditions that promote PAH growth. Could we take that into account with reactive molecular dynamics simulation?
Well, yes, that's what we've been trying to do. Okay, there is of course always. We believe that for the simulations we did, the reactive potential was accurate enough. But if you were to look at, for example, oxidation and other interesting processes, then it is unclear whether the current reactive potentials are good enough to do these simulations. Yeah, that's what I want to say.
Okay, thank you. The second question is from Professor Coles. There are several very recent papers claiming to understand the complete formation process, or at least to understand which parts of the mechanisms would be the most important ones. It's hard for those not directly involved whether these explanations are agree or are mutually exclusive. Regarding the present status of the fundamental understanding of soot formation, can you comment on how much of the reaction chain from the molecular state to the incipient particle is encoded in the structure of the fuel molecule, and how much is dependent on the reaction surroundings, like a pressure, mixture fraction, residence time? Further, do you have some decisive experiments on your wish list to clarify such issues?
I mean, there are several things to say. Okay, number one, there are many parameters that influence this process, and we know that at high pressures soot formation is enhanced. Okay, and that's clearly because collision is enhanced, and so that will play a role. And specifically, if there is a physical mechanism involved, you will see it. Okay, but unfortunately, also you'll see it if it's just chemical. We believe that the formation of 5-member rings plays an important role. And Maureen, together with Young Ren, has just published a paper where we could at least qualitatively show that if we have a fuel that promotes 5-member ring formation, that then you see a higher sooting propensity. This was just one experiment, and it needs to be supported by other observations, but we believe these 5-member rings can play an important role. I mean, as you see, at various points in time, we thought that we knew how it works, okay? And then it didn't, okay? So we thought for a time, oh, the flexoelectric effect, that must be it, okay? And then, oh no, it's not strong enough. And at the moment, the latest flavor is, these pi radicals that form this sort of pancake bonds where the dispersive forces and the bonds sort of stabilize the dimer. If that turns out to be a key molecule in the inception process, then of course the formation path of these 5-member rings will be very important. And every reaction network that leads to this path will have to play a role. Of course, that basically means that the pyrolysis products of the various fuels that sort of support that formation will be more sooting. It would be, of course, nice to show this.
The following question is from Junxia, one of our panelists. How do you see the way ahead to incorporate all these exciting smaller scale simulation findings into macroscopic CFD approaches to predict soot?
This is a good question. If we were to identify the mechanism correctly, which we haven't identified at the moment, if we also then were able to quantify this mechanism, if it then turns out that you can reduce the model accordingly. And if the gas phase is sufficiently robust, then you can, of course, come up with some sort of numerical approximation that you can then put into a CFD code. There is a lot of ifs. I can tell you, we also do engine simulations. I have a company, CMCL, and we've been working with OEMs, and I can tell you what we do. We we basically do sort of a mixture of detailed chemistry and a lot of fitting over a whole operating range, right? Sometimes accompanied with machine learning. So I think, to be honest, by the time we understand how this formation process actually works, we will have come up with a fudge for CFD that is good enough. And there is also, of course, the possibility that the interest in at least reciprocal engines will sort of fade away. It'll be certainly important for the gas turbines and possibly for material synthesis. In that respect, these simulations will be also important in the future.
How do you think the experimental measurements on particle sizes between 1 to 3 nanometers could contribute to our understanding and also simulation?
As I said several times during my talk, without the Dana work with the IBM group of the high resolution TEM, we wouldn't have had the motivation to look at the interaction of the molecules, because now we know that they're there. In my view, these experiments are super important.
The next question is from Matt Cockett. Have you ever considered using your tools to predict how a particle might evolve during a sampling process as it is extracted from a flame and undergoes a rapid temperature drop, followed by a long time, 2 seconds to days, before analysis of the particle? This is also a question I'm curious of. Thank you.
We haven't used the molecular dynamics code, but we have done this in the kinetic Monte Carlo code coupled to a method of moments. And what happens is, because of the temperature drop and the pressure loss, the whole process freezes, and there is not a lot of interaction. That is at least what it was quite some time now ago, and I may not remember everything in detail, but the bottom line was nothing happens, not a lot.
Okay, thank you. The last question from Xiao Jiang. As you mentioned in your previous potential energy study, the small pH molecules shows thermal instability and are unlikely to form the soot where small pH. The question is why we can use small pH pyrene as the soot core, and the structure seems stable enough at high temperature.
If you take pyrene and put it in a flame, it's not stable. It doesn't form particles, okay? Yet it forms the inception species in many computational models. So what basically means is that pyrene is not pyrene as the molecule. It is a surrogate species that represents whatever is responsible for this process, okay? And the rate at which it, basically the inception rate is a fit, okay? And what we will probably find that the bottleneck of this inception species, once we know what it is, will be of the order of that rate, okay? But it won't be pyrene, it'll be something else.
Here I have another 2 questions, and one is how important is the contribution of small aromatics to inception, given that they are significantly higher concentration?
This is the good question. Okay, clearly there will be a lot of small aromatics connected by aryl bonds, okay? There will be, but the question is, what is the chain mechanism? Clearly we know soot forms, and it forms quickly. And So what we need to have is some sort of a polymerization step. If you ask me what this step is, I cannot tell you. I do not know. Okay, but we may have identified some candidates for a possible inception, but how this process then acts so quickly to grow the structures, this is still unclear. It is maybe it's clear to others, but it's unclear to me, right? So we are working on this and trying to use different hypotheses on how this could happen.
The last question and a request from Professor Katarina Coles. I know that you use real-time monitoring of emissions in Singapore, especially emissions from ships. Can you briefly introduce us to this work?
You see this little thing, the red thing here, this is Marina Bay Sands Hotel, okay? I am sitting, you can't see the building, I'm sitting at the moment here, right here in a hotel room under quarantine. Yeah, I've been in this room for the last 10 days, they don't let me out, okay? So the black dots here, that represent ships, okay? And so we working on something called Knowledge Graph, it's the World Avatar Project, in which we basically connect all these models in one big attempt using this knowledge graph. We have just, if you're interested in that type of work, I can only point you to our website and look under knowledge graph. We've just, you know, the ultimate attempt is the vision that Michael Franklach presented in Heidelberg in 2006. The symposium there, where he gave his prime lecture and where he basically painted this future. And this is what it's all about, a full automation of the model development. And here we have now bought some sensors. We are measuring these emissions. And the idea is that we use a combustion model in each ship. We use the real-time information where these ships are. And from that, we basically calculate what a virtual sensor would measure and compare this with a real sensor, so that we have a completely virtual representation of the world. So anyway, thank you, Katharina, for asking this question. I will not say any further. There are some nice papers on the knowledge graph on the COMO webpage.
Okay, Professor Kraft, thank you so much to give us this wonderful webinar.
Thank you, Markus.
Thank you.
That was a great talk.
Thank you.
Thank you, everyone.
Good seeing you. Yes.
Yeah, see you
Bye.
later.
Thank you, Markus.
Take care,
Thank you,
everyone.
Markus.
Bye-bye.
Bye-bye.
Everybody,
Take care.
Bye, Kelly.
keep healthy.
Bye-bye.
Bye-bye.
Bye-bye.